Hi, everybody. Welcome to Phys 4250 or 8250, Design and Application of Lasers, for Wednesday, September 16th. I'm your instructor, Dr. TJ Hammond. In this lesson, we will be covering Chapter 2, Atoms, Molecules, and Solids, from sections 2.1 to 2.5. So, if you remember from Monday, the daily assignment was for you to discuss that you had some two-level system where you had a lower level 1 and an upper level 2, and you'd have some atom sitting in this system. And it turned out what we wanted to do was have some photon come in, and we'll draw this photon as some little squiggly line here, and that excites this atom up to the second state. And then we come in later with another photon, and that takes this atom back down. And so what you get out are these two photons. But the question was, what are these states? So physically, this has to have some kind of gain medium. And so there has to be something that's absorbing these photons, there has to be something that's emitting these photons, it has to be something physical, of course, right? And so the daily assignment was to understand where these energy levels come from. So that's actually going to be the point of this lecture. So for those of you who have the textbook and are reading ahead, you'll realize that section 2.2 is basically what your daily assignment was. So to talk about these quantized energy levels, we can do a full quantum mechanical description. I'm going to very briefly gloss over that. Typically, people start off with this Bohr atom, and that's because you get pretty much the right energy levels, the right energy values for not too much work, for something that we can do as even a first-year student. So this is called the Bohr atom. So this was proposed in around 1916 or so by Niels Bohr. Quantum mechanics had not been developed yet. Of course, that was with Heisenberg and Schrödinger, which would happen about 10 years later. But Max Planck had come out in 1900 saying that light can be quantized, and the energy of this light is proportional to its frequency, where that constant of proportionality is given by the frequency, the angular frequency. So that's E is equal to h bar omega. And then also Einstein's photoelectric effect also reinforced that as well. So what Niels Bohr did was he came up with the idea that the electron that's sitting here as a planet is orbiting around this proton in the middle. And it's separated by some distance r. We don't know what that distance r is yet, but it's orbiting around like a planet, so moving with some velocity v. Now, all we need to do is find out from Kepler's laws, or even or Newtonian mechanics, what the energy of this is going to be, and everybody would know this for hundreds of years. And you would say that the centripetal force is going to be negative mv squared over r, and you have this the thing that's supplying the centripetal force is well, I guess I have it as gravity, but that's because it's a planetary model. I guess I should actually say that this is Coulomb, so I'll call this Cool. And that Coulombic force is negative 1 over 4 pi epsilon naught e squared over r squared. And so to get the potential from that, you integrate negative f dot dr, and that gives you negative 1 over 4 pi epsilon naught e squared over r. And I'm sure from second year mechanics you remember this. So that means that the total energy of the system here is going to be 1/2 mv squared plus the potential energy, and so it's 1/2 mv squared minus 1 over 4 pi epsilon naught e squared over r, where epsilon naught is a permittivity of free space and E is the fundamental charge of an electron and the proton, which happen to be the same, just opposite sign. But at equilibrium, that means that this electron here is just sitting happily at this distance away. And so that means that there's actually no net force on this. And so the Coulomb force is equal to the centripetal force. And I realized I put a G there as well. So I'll put a Coulomb force. And so we get mv squared over r is equal to 1 over 4 pi epsilon naught E squared over r squared. And so one of those r's cancel. And we get 1/2 mv squared is 1/2 E squared over 4 pi, or 4 pi epsilon naught r. But of course, you know what 1/2 mv squared is. That is going to be the kinetic energy. So the total energy of the system is the kinetic energy plus the potential energy, but you found from the previous slide that the potential energy is this, and the kinetic energy is 1/2 of that, but of the opposite sign. So that means that the total energy is negative 1/2 E squared over 4 pi epsilon naught 1 over r. So that is well understood. People would have been able to calculate that, 400 years ago or 300 years ago, though. But what Niels Bohr proposed, his postulate, basically his guess, was that h bar has units of an angular momentum. And so he says, what if, since we have this energy is proportional to frequency by this by Planck's constant h bar, or h over 2 pi, what if this angular momentum is actually just quantized? He had no reason for believing this. This was his guess. And so he said, okay, since h bar has units of angular momentum, let's just say it can only be 1, 2, 3, 4, whatever. So if you remember from a definition of angular momentum, the angular momentum is r cross p, or just the magnitude of it is going to be mrv. So we can then convert that to what the kinetic energy is. So 1/2 mv squared, since we know, since we have this in terms of v. So we can say 1/2 mv squared is L squared over 2 mr squared. So what that means is we can now put that into our energy equation from before. And so we have L squared over 2 mr squared is equal to 1/2 E squared over 4 pi epsilon naught 1 over r. So what that gives us for r is that it's L squared over m, and then the inverse of E squared over 4 pi epsilon naught. And so that means that r is equal to n squared h bar squared over m times the inverse of E squared over 4 pi epsilon naught. So E squared over 4 pi epsilon naught, just some constants, h bar squared, just some constant, m is the mass of the electron. And so but what this is telling us is that r, this radius, this distance from the electron to the proton, is going to be quantized, and its distance is proportional to n squared. So r is now quantized, and but the thing is that you plug that back into the energy equation, and energy is negative 1/2 E squared over 4 pi epsilon naught 1 over r, and put a little subscript n since it's quantized by n. And so we substitute that value in, and we get that the energy of the Bohr atom is negative 1/2 E squared over 4 pi epsilon naught, and that's all squared, times m over n squared h bar squared. So that's what he came up with. And it turns out that this model is not correct whatsoever. You've probably seen this before in first year, you've probably seen this in chemistry, maybe even high school, because it's very simple to derive. You just have that one postulate, you say you guess that they're going to be bound by some Coulomb force, and that this electron is much lighter, so it's going to be orbiting around this much heavier proton. And then from there, the only thing that you have to recognize is that the angular momentum is going to be quantized. It turns out there's a whole bunch that are wrong with it, but it does give this right energy value, and that's why this is still taught. If you look at the lowest state, you can't have n is equal to 0, and that's because this energy blows up. That's, I guess, that agrees with quantum mechanics. But you can have this n equals 1 state, and so that's this closest orbital here, as shown as n equals 1, and then something that's going to be 4 times farther away will be the n equals 2 state. And of course, that energy will be much lower. So why this got so much attention, though, is because it actually accurately predicted the transitions, the energy transitions, as an electron went from this state and decayed down here. This released a photon of energy of around 7 electron volts, which is slightly in the EV, in the UV. And that was right, and it turned out that these energy levels are quantized. So this is a very crude model. It gives approximately these right numbers. It turns out it's not right at all physically. So once you stick in a second electron, you can't get this to work whatsoever. The angular momentum, he's pontificated that the angular momentum is quantized, which is true, but the angular momentum is actually completely wrong. The n equals 1 state actually has no angular momentum, but this obviously has to have some angular momentum. Okay, so I'm trying to emphasize that it's not a correct model, but it does give us the right energy values. And that's for those of you who haven't taken any quantum mechanics. This is what the origin of, or this is kind of a way of modeling the quantization of these energy levels of the electron in an atom. So more completely is the more complex, fully quantum mechanical model. Oh, it seems like this is not loading properly for some reason. There we go. Okay, so if we actually use quantum mechanics, what we get is this potential. So of course, the potential, just as we've shown before, is, well, I guess I can actually say what it actually is. Negative 1 over 4 pi epsilon naught E squared over R. And so that's what I've drawn here. This potential, I've taken a cross section of this potential that goes as 1 over R, right? And it's negative, okay? So a potential that is less than 0 tells you that you have bound states. That's the convention, okay? Well, I'll just stick with that for now. Okay. So now quantum mechanics, we have to solve this full 3-dimensional Schrödinger equation. You can actually simplify it so that it goes down to 1 dimension. But you can see that you have second-order derivatives with respect to this radial function mu, and then you have the potential negative E squared over 4 pi epsilon naught 1 over R. So you still have this same radial potential. But then you have this second term h bar squared over 2m L plus 1 over R squared, and that happens to be the centrifugal potential that, if you remember from second year mechanics, that we have this effective potential, and that is part of the effective potential term. The L plus 1 is the quantized angular momentum, the actual proper quantized angular momentum that is not dependent on what Bohr had postulated. And you have to solve this differential equation, and it turns out this differential equation only has certain values, and it's quantized. So for those of you who are taking quantum mechanics this year, I'll let Dr. Razy show you how to do this. If you've already taken quantum mechanics, you've already struggled through solving this differential equation using power series and things like that. But basically, quantum mechanics is called quantum mechanics because these energy levels are quantized. So in classical mechanics, these electrons would be able to sit anywhere, just like planets can sit at any orbit that they want. But in quantum mechanics, these energy levels are quantized, okay? And so they sit at these discrete energy levels. And so what we do is, or what we're talking about for these discrete levels for these states is we'd have an atom sitting at this state here, and we could have a photon coming in, and I'll make it blue, and that photon would excite this electron to some energy that you want, and so that one's going from the first to the third state, and so now that's sitting up here. Oop, I think I might have lost the feed for a second. Okay. And now we could come in with, say, a different color. Maybe I'll come in with green, and I come in with a green photon, and I can de-excite this atom or this electron so that it's now sitting in the n equals 2 state. So it went from n equals 1, this ground state, up to n equals 2. And we've done that by this transition with these different photons. So that's where these states come from. That's where these electronic transitions come from in an atom, is that we have these discrete quantized energy levels due to the Coulomb potential. And so, good. All right. So that you should be familiar with. Something you might be less familiar with are the energy levels in molecules. And so now, for say example, you have a hydrogen molecule, or nitrogen or oxygen, some diatomic molecule, and it turns out that this will be always vibrating with some mode. This vibrates out, and then this comes in. Now, classically, of course, this is just a harmonic oscillator, and you can move your mass on your spring as far as you want, and this thing can oscillate. It'll always oscillate at the same frequency, but it'll oscillate at the same amplitude. Sorry, at different amplitudes, but always at the same frequency. It turns out with quantum mechanics that's not totally true. So I've shown the potential on the right here. What you have is that if the atoms are too close together, then they actually start to repel each other, of course. But if they're too far apart, they attract one another. But the problem is that when they're infinitely far apart, they don't interact. So this isn't a complete parabola. And so a perfect parabola would, of course, look something like this. But we don't have that, because if these atoms are pulled apart to break apart this molecule, it's not as if there's an infinite amount of energy that's trying to pull these things back together. They just don't care anymore. So that's why this thing curls off and goes to 0 when r approaches infinity. Okay, but again, we have quantum mechanics. So what we do is we have whenever whenever this energy is less than 0, we get these bound states. And so these bound states, as we've described before, are quantized because it's quantum mechanics. And so we get these discrete transitions. Now, in this region at the bottom, this is it's pretty well represented as a harmonic oscillator. So this is approximately harmonic. And people have solved this almost immediately after Schrödinger came up with his equation. People solved the harmonic oscillator. And it turns out that for these low energy states, the energy separation of these first few states is that this delta E are all the same, which is kind of interesting. But then as this potential diverges from being parabolic, these states become increasingly close together. But they're still quantized until it's a free particle. So what this is saying is that we have discrete vibration modes of this object that's oscillating back and forth, and these vibration modes are quantized. So the energy from going from one vibration mode to the next one is going to be quantized. Now, as I said in the previously, for here we have like a blue photon to excite from the first to the third state, and then a green photon from the third to the second state. Those are approximately the right colors. That say for like a hydrogen atom, this is somewhere around a few electron volts, as in this is going to be happening in the visible or maybe even in the ultraviolet transition. But if we're dealing with vibration modes, these are all happening in the infrared. And really small molecules, so like CO2, H2O, N2O2, those vibration modes all happen in the mid-infrared, so something between 2 microns or so to about 4 microns or so, depending on the weight of the atoms, the strength of the bond, all that kind of stuff. If it's a single bond or double bond, all that kind of stuff. So those all happen in the infrared, and lasers still, we still call them lasers when they're in the mid-infrared. But we also have the rotational motion, and so that's the rotational motion of these molecules. And so these things can be spinning around in space, but again, things are quantized because it's quantum mechanics. And so I won't get into the derivation or anything, but you end up with this h bar squared over 2I j plus 1. If you were paying attention before, when we were talking about this effective potential, we had h bar squared over 2m L plus 1. That L was the angular momentum quantum number. Now we have the total angular momentum quantum number J. That's what that's representing, but J is also quantized. And so that means that the energy levels of this rotation are also quantized. These rotations happen in the far infrared though, so they tend to not be very good for lasers. Some molecules, they can be kind of in the near or mid-infrared, but they're typically not, they're typically quite slow, picosecond to nanosecond, especially for very large molecules. They'll be, nanoseconds or even microseconds. Okay, so for the daily assignment, read section 2.7 on conductors and insulators for Friday, September 18th. And I guess I will see you in lecture.